Hello, everyone. My name is Saeed, and in this part of the presentation, I just want to give you a high-level idea and overview regarding ASTRA-sim structure and how it works. So, if you recall from the previous part of the presentation, we have different levels that are involved in designing distributed training platforms: workload layer, system layer, and network layer. And the main motivation for us to build ASTRA-sim was that once we uh, reviewed the available tools, we found that there are many open source network simulators available, but there are not too many tools that actually capture the workload layer and the system layer aspects of distributed training workloads. So what we did was actually building this workload layer and system layer that is called ASTRA-sim, which is portable on different network simulators. So uh, that's uh, that's uh, that's how the idea of ASTRA-sim is motivated. Now, if you and if so, this slide actually shows the high-level structure, the software structure of the ASTRA-sim. And so let me actually see if I think my cursor is not okay. So now I think you can see my cursor as well. So here on the right, you have the software architecture of ASTRA-sim is a workload layer on top of a system layer. So these two components form ASTRA-sim, and then we have a network API, which is an interface between ASTRA-sim and any network simulator that supports this very lightweight network API. And each of these layers actually has their own input parameters: the workload layer, system layer, and the network layer. So the workload layer basically captures these workload characteristics, distributed training workload characteristics, such as the parallelization strategy, and also some orders in which we execute these computation and communications. And it is fairly easy to add new training loops to it. And on the other hand, and we support two different workload front ends. So we initially started with a text-based workload engine, which basically you can describe the workload using a text representation, which is very easy to understand, but has its own limitations in terms of very sophisticated workloads that have complex interactions and very hybrid parallelization strategies. We felt the need that we need to make it more um, detailed. So we came up with this execution graph engine as well, the EG part, which these two different front ends are described in the next uh, part by my colleague Taekung. But just here, I just want to mention that we have two different front ends, and then the second front end, the execution graph, is actually more detailed, and all different complex distributed training workloads can be expressed using this representation that we developed. Now, we have and then the other part of the system layer, the other part of the system is the system layer, which basically deals with defining the communication library and how you schedule communications and other system level aspects of the platforms. So here you can think of it as a layer that, for example, captures the communication libraries such as NVIDIA Nickel, and it supports various types of collective communication library, collective communication algorithms, and different ways to schedule the collective communications. And on the network side, what we have is the different backends that we developed, and some of them we entirely developed, some of them we just added the network API to it so that it works with ASTRA-sim. So the analytical one that we developed is actually a very fast network backend that is used to iterate over thousands of design points in a very fast way, but it has its own limitations, such as it sacrifices accuracy when we have communication patterns that have congestion. Then the second backend is Garnet, which is most suitable when someone wants to design distributed training on top of network on chip. So you have multiple compute units and that are connected together using network on chip, or we have multiple dies that are connected through the on-package interconnect. So because the nature of a Garnet is that it best models these types of networks. So in order to study the distributed training on such environments, one can use Garnet for that. And then we have the NS3. This is our newest network backend that we support, which basically models the data center, the wider data center network, which basically one can now model distributed training platforms that are connected through RDMA over Converged Ethernet RoCE, for example, network, or other RDMA NICs that support, for example, InfiniBand fabric. So NS3 is best suited for studying distributed training workloads across a data center. Now, the ASTRA-sim architecture is as follows. When one ASTRA-sim experiment starts, depending on how many GPUs or any NPU that we want to model, ASTRA-sim workload layer and system layer are instantiated for each of those NPUs, and also one instantiation of the network API. And these instantiations form the NPU 0, and for each NPU we have a separate workload layer instance and system layer instance and network API instance. And these instances then, using the network API, then talk to the network fabric, which is modeled through the network simulator that is the bottommost layer. So this is how, from the software perspective, ASTRA-sim experiments will be executed. Now, here is just a root directory of ASTRA-sim. So the code is inside the ASTRA-sim subfolder, and then here in the build, we have the scripts to build ASTRA-sim with different backends. And we have some set of examples here, some example run scripts. And here are the external sub-modules. For example, the different network backends are cloned. And the inputs, we have different inputs for workload layer, system layer, and the network layer. And then we have some additional tools, such as workload generator that I briefly described, that one can automate the workload generation input files through this tool. Okay, so I don't go to this slide because it relates to the network backend, which will be covered by William. But here I just want to talk a little bit about the ASTRA-sim run scripts, which basically is if you look at the sample scripts that we developed, here there are a bunch of options that are available when someone tries to call ASTRA-sim execution file. And here you can pass the network input file, system input file, and workload configuration to just tell the ASTRA-sim execution binary that these are the paths for different inputs, and also the path for dumping the stats, and also some other additional information that you can find more details in the ASTRA-sim GitHub page. Okay, so I just want to briefly talk about the kind of reports that one can expect to get from ASTRA-sim after experiments. And here is a sample report that is generated by ASTRA-sim after running a ResNet training for multiple training iterations. And here you can see the ASTRA-sim can generate a layer-wise stats. For each layer of the ResNet, you can then get the breakdown of the compute times, communication times, and exposed communication times. And here is just a run name that you have defined during when you are calling the exec file. And here are the different compute times that are executed to calculate the forward during the calculate the forward activations, and also the gradients during forward pass and back propagation. And then here we have the total communication time. So depending on the parallelization strategy, for example, if you have a data parallel, then whenever each node generates the local weight gradients, it needs to do an R reduce between other nodes to get the global gradient summation and then update the model. So these are the communications for different phases. So because this workload was in a data parallel, it only had weight gradient communication, so we didn't have any communication during the forward pass or input gradient computations. So the only communication we have is after the weight gradient computation, and this is the total communication time for this layer of the ResNet. And here, depending on how we can overlap the compute with communication, some of the communications might be overlapped with the compute. So here we come up with a term called exposed communication, which basically means the amount of communication that is exposed and was not overlapped with the compute. And here in this very specific case, almost all of the communication that we had here is exposed. So it means that we were not able to overlap this communication with the compute, and therefore the entire communication is actually on the critical path in this very specific example. And then here on the right, we have, here we have the results in a layer-wise manner. And then you can also get some total compute and exposed communication times, which basically, if you sum these two values, you get the total training iteration latency. So it's just a summation of all layers exposed communication time and all layers compute times. Now, in addition to that, end-to-end.csv that ASTRA-sim generates, you can also get very detailed communication breakdown results as well, depending on the algorithm, communication algorithm that you use. Basically, these are the configurations that one can set in the system input file. You can get various very detailed communication latencies. For example, here we have used a communication algorithm that uses 5 phases. And in each phase, we just are interested in determining the average message latency when we inject a message into the network. And these stats can give you the layer-wise, again, delays for each message that is sent out to the network. So I don't go into the more details about this. I think most users probably find this end-to-end CSV enough to get their desired results, but there are more detailed results also reported by ASTRA-sim, which we put all these explanation for these different stats in the GitHub address for this project as well. So let's now visualize the kind of stats that one can generate through ASTRA-sim. And in the next set of slides, I just show you the kind of graphs that one can generate through these results. For example, this one is raw communication latency for running ResNet on some distributed training platform. And here you can see the layer-wise total raw communication latencies for each layer. So each of these layers, because it was in a model parallel, each of these layers, when we compute, it has its own weight gradients generated during the backpropagation, and those gradients needs to be all reduced. So that's why you need to communicate those weight gradients, and therefore each layer has its own communication operation. And here you can see the raw communication operation for that. However, as I discussed earlier, those communications might be overlapped with compute. And in this case, all of these communications for all the layers except the layer 1 is actually overlapped. So we don't have any exposed communication here. So exposed communication is the yellow bar. And only the first layer has a exposed communication of this latency. And also you can put the compute times side by side of the exposed communication to get an idea of how much you are stuck with communication operations and how much you are stuck with compute operations. So you can get a sense of the balance between your compute efficiency and communication efficiency. And also you can, if you want to use those very detailed results, you can then get some interesting but very detailed communication reports. So the description of this is actually explained in the ASTRA-sim original paper itself. So I don't go into the details of this here because of the time constraints. However, just very briefly, what it's trying to convey is that because this detailed diagram basically tells you what percentage of the communication delay is spent on what phase of the communication algorithm. And then you can see what phase of the communication algorithm is basically has the most overhead. And then one advantage of using ASTRA-sim is now then you can use it to study the trends. For example, what happens if my distributed training platform increases in size? And here it's showing an example of 3D torus, and here it shows what is the ratio of exposed communication and total computation as you increase the total number of GPUs. So it is showing that, and it is also expected that as the number of GPUs increases, then your communication overhead becomes larger and larger, and then more percentage of the total runtime is spent on the communication. And then also you can now find out that, okay, what happens if my compute efficiency increases by some X? So here it shows this breakdown of exposed communication and computation, and then you can see that, okay, if you get 2x better compute efficiency, meaning that all your compute latencies, if they are half by 2x, then you can see that the total communication latency is also increased, because the reason is that now you have less compute to overlap the communication with, and therefore the ratio of exposed communication also increases. Okay, so in the last part of this part of my presentation, I just want to briefly talk about the workload generator. Basically, it's one of the tools that one can use to generate the workload input files automatically. And currently, it just works with the text-based workload engine. So it's not working. It's not compatible with graph execution engine so far, and it generates workloads for this front end. So basically, the user can basically define the compute times in terms of the matrix multiplications and gem operations, which are the most significant overhead of the distributed training compute times, and also determines the parallelization strategy. And through that, so here is a sample run script for that. So basically, the compute operations, the global compute operations are described in an input file. And also here, you can determine the parallelization strategy. In this case, it is a data parallel. And then this workload generator basically uses compute simulators that currently it is ASTRA-sim to get the runtime overheads for these compute operations, and also split these operations depending on the parallelization strategy to different NPUs, and also automatically calculates the communication operations and communication sizes for that specific workload and parallelization strategy. And here is the ASTRA-sim, which is a separate project, but is used in the workload generator to get the compute times. And ASTRA-sim, the ASTRA-sim has its own detailed parameters. For example, the specification of your accelerator, whether it's memory SRAM, and also SRAM capacity, and also the compute capability of your simulator. So you can tune this ASTRA-sim to get you the exact compute times for your target accelerators. And that was a very high level overview of ASTRA-sim.